All right. Hi, everyone. So, as part of the NGIT Robotics Club, one of the things that we really want to look at is robotics research. But robotics research can be a bit intimidating. And also, unless you're really into the field, it can be hard to know why stuff is cool. And so, really, the goal here is to look at robotics research from the perspective of, more of a detached perspective where you might not know the background required to understand why things are cool. And so, really the goal here is to introduce people to the basics of robotics research and cover some of the most important and some of the most cool research that has come out. So the paper that we're going to be discussing today is called Programmable Self-Assembly in a 1,000 Robot Swarm. This was a paper written by Mike Rubenstein. Got the other authors there, but Mike Rubenstein was my PhD advisor, so I'm pretty familiar with this paper. So one of the subfields of robotics that I personally think is the most cool, also have pizza, is called swarm robotics, which is where you have many robots operating together in order to perform some task. And in general, you have to use a lot different sort of thinking in order to accomplish these things, because unlike traditional robots where there's a very clear mapping between I want you to move there, pick this up, do that, in general you can't give very specific commands. You kind of have to make it so that robots accidentally do what you want them to do. And if there are any questions at any point, just let me know and all kind of stuff. Well, we'll start out by watching this video because it does a pretty good job of showing what this is all about. So each of those little specs you see there is a robot. It's called a kilobot, and what they're going to be doing in this paper is they're forming shapes. And so the real question is, how do you do that? How do you tell these robots to form a shape? Despite the fact that they don't have GPS, they can't talk at long distances, all they can do is talk to their immediate neighbors. And what you see right there is basically everything that happens, right? So the robot is moving, and the robot is sensing the distance to other robots. Other than that, the robots can't really talk or do anything other than those very limited things. And yet, despite that, they're able to form these shapes, right? So the question is, okay, what rules would allow such simple robots to do that, right? Can anyone guess? No, it's hard, right? Like you can't point to any single rule that would let them do that. I mean, theoretically you could say, okay, this robot moves to this point, this robot moves to this point. But even then, like, how does it know where it is? How does it know, what direction to move? It's really something that you can't like just hand wave away. And so a big part of what this paper does is it looks at the algorithm that enables this sort of self-assembly. And we'll go over a lot of this stuff later on the specifics, but in general, what it is that these robots are simply going to follow the edge until they're inside the shape. Once they're inside the shape, if they would leave the shape, they stop, right? But you can see this is what it looks like when the robots are actually forming these shapes. Now, what's kind of funny is that in all of these algorithms that they do, they're always going around the shape clockwise. And so because they're turning more to the right than to the left, their left motor is actually burned out more. And so all of them have trouble turning to the right now. But you can see, right, it takes 12 hours for one of these experiments. So, as I said, how you go from simple robots to these high-level results is really the big question of swarm robotics. And really figuring out how to kind of make these robots accidentally do what you want them to do, is kind of how I describe it. That's really the big challenge. So this paper essentially goes over one algorithm for doing that. Self-assembly in general is a field that is really looks at, if you've seen these videos of ants forming bridges, right? That's self-assembly. If you've seen Big Hero 6, right? That's self-assembly. And so doing it in the real world requires a balance of, robot capabilities and robot algorithms. And in general, if you're making 1,000 robots, which they did here, and I believe it's still the biggest swarm that's been deployed, adding a $1 sensor is going to increase the cost of the swarm by $1,000. So you really don't want to add a $1 sensor. And so a big part of this paper is really reckoning with the fact that you have 1,000 robots, right? You can't have wheels, right? Instead of wheels, they use vibration motors. And so going through this is the science robotics paper. Science is a great place to actually look at a lot of these more famous papers. A, because it's a very highly regarded journal. B, it's also aimed at more of a general audience, and so they tend not to go into the real algorithmic side of it. But they start off, they talk about the biological inspirations. Biological inspirations are a huge part of swarm robotics. Everything from the distributed delivery of blood throughout your body, to cell growth, to ants foraging in a forest. These are all examples of swarm behaviors. And what's interesting to think about is that you arguably have more examples of swarm behaviors to draw from than you do individual behaviors when you're looking at behavior design. When you're talking about nature, right? I mean, societies are arguably swarm systems. And how do you design a society? Well, I think we're still figuring that one out. Hopefully we figure it out soon. Reading the news. Anyway, but the other thing you have to look at, and they talk about it kind of here, is computational tractability, right? Is what you're going to propose easy to run, right? These robots are using very low power chips. They're using the Atmega 328. I believe they're using the 328. That's the chip that you use in the Arduino Uno, right? Not very powerful, but it's cheap. You can get one for about $1. So it's very cost effective. I think in total this robot has an overall part cost of $20. Right, so you can see the overall parts here. You have little vibration motors, and if you've seen BristleBots, right, you're kind of vibrating, that causes forward motion. Use the same thing. Again, this is a cost consideration. A traditional motor is going to cost you $3, $4, $5. Vibration motor you can get for 99 cents on DigiKey. It's not as good as a regular motor, but if you're concerned about cost, it's what you need to do. They had a custom PCB, everything's mounted down there. You got a little coin cell battery there. How they actually charge these is an interesting thing to talk about. Can anyone think of how you might charge 1,000 robots?
Electricity, clamps on a big aluminum sheet, put it on top of all the robots.
That's exactly what they do.
Yeah.
So, the legs here are connected to ground. This top thing is connected to, high voltage, whatever. I think like 5 volts. And yeah, you got to consider, if you have one robot, how are you charging it? You're plugging it in. Great. Okay, let's time myself. Okay, I go down. So pick up the robot, take the robot. Okay, let's get it. Okay, here's the plug. Plug it in. All right, I got it plugged in. Put it down. Okay, that was 7 seconds. Okay, that was 1 of 1,000. Let's be kind and say it was 6 seconds. 6 times 1,000, well, that's about 100 minutes. So about an hour every day of plugging in robots. Okay, well, now I have to unplug them after they're done. So that's about, 3 hours per day of plugging in and unplugging robots. That's not great. That's not great. That's something that's really unrealistic. And now you need like 1,000 cables and everything, right? So as what's your name? As Simon pointed out, right, you need some way of doing everything in massive parallelism. And so, yeah, what they do is they literally just have aluminum sheet, and they charge them all at once. What this means is that you can't have external charging stuff. Like all the robots have to manage their own battery levels and everything like that. But ultimately, that's something that you have to do, right? That's a cost that you have to incur so that what you have is reasonable. You can also see how they communicate, right? They're on these long legs, and they have little IR diodes, kind of like a TV remote, where they're just bouncing it off the floor, and that's how they're sending, receiving signals. They actually overdrive the little LED, where the LED is rated for like half an amp, and they're running like 3 amps through it. But because they're doing it like for a very short amount of time, they it's not an issue. But they actually have like safety stuff in there where if the LED is on for more than 1 millisecond at a time, the entire robot will shut off. Because otherwise you burn out the LED because they're driving it at way beyond what it's rated for. But it apparently works out. And there's a lot of like information, a lot of analog filtering happening with that thing. And here's a little hint for reading academic papers. Just look at the figures. Like any good paper, the authors are going to spend a lot of time on the figures, and you can get like 60% of the information just by looking at the figures and the captions, right? And so this one does a really good job of kind of showing the overall robotics system. And again, you could read all this, or you can look at this really nice figure that describes how the robots are actually making all their decisions. So what you can see here is that you have a few robots that you say you are at 001001, essentially, right? You're a bit different because it's in a triangle. Those are the only special ones. You can imagine if I know how far away I am from 00, that will tell me the overall position within the structure. And so there's this concept called hop count, right? And a hop count is essentially how far away you are in terms of, how many communication hops you have to go through. And so you see here where these ones are hop 1 away from the seed. This one, it's 1, 2. This one, 1, 2, 3, because there's a little gap there. This one, 1, 2. And so, for instance, if you're the seed, hop 1, hop 2, hop 3, hop 4. Kind of looking at how many immediate neighbors you have to go through. And this is something that's actually really easy to get out of like very local communication, because all you have to broadcast is, this is my hop count. The other one says, this is my hop count. And from that, you're able to build out these coordinate systems, and you're able to figure out where you are relative to the 0 location. You can also do some refinement on this because you don't just have the hop count information, you also have this distance information. Remember that you're bouncing messages off of the floor. And so if you're looking at the intensity of that signal, that's a really good proxy for the actual distance, right? If it's at half, if the intensity is half of what it is when you're right next to each other, maybe that means you're twice as far away, roughly. I mean, it's a quadratic fall off, but roughly that. And if I remember correctly, you can get some pretty good estimates of how far away you are. It's within like a centimeter or two. And so you can synthesize all this information into a pretty reasonably good position estimate, right? If we're looking at this again, and we're looking at these shapes that they're forming, you can see that there's some error, right? There's some error in the overall position estimation, and you can see that as basically the skew that you have here. But overall, I mean, from here to here, if all the error you have is, maybe a few robots in length, that's pretty good. I'd be happy with that. So this is all the general aspects of it, where you start out with a given shape, right? You have this black and white image that you feed into the robots, and from that you're putting in this ability to measure distances, and then all that's really left is going from these concepts to the actual shape formation, right? And in order to do that, as we saw in the video, you're following that edge, right? And so all robots do is the one that's furthest away, right? So it's looking at the hop counts, right? The one that's furthest away, it knows that it starts out outside the shape. It goes. It says, okay, I'm inside the structure. And then because it's constantly updating its positioning, right? If it says, okay, I'm inside the structure and I would leave the structure, therefore I stop, right? Then this one comes along and it says, oh, I bumped into someone who has stopped. And eventually what you're going to do is you're going to fill up this entire row here. And that's going to give you one layer of the shape. So going back here, let's just kind of use that as a starting point, right? You're seeing everything move, and you can see they're building it up layer by layer, layer by layer. You see this pattern emerge where it's moving on the outside of the shape, it enters, it creates this layer. And again, you see the robots, they're not moving to any particular position. And as I said, you're basically you're making them accidentally do the thing you want to do, right? The mapping between I want to make a shape and this, it's pretty non-obvious. And if I just told you, this sort of algorithm, and I said, is that going to work? I don't know, right? And that's really one of the big challenges of distributed systems, is that it's very hard to know what behaviors will result in this macro level stuff that you want to do, and also like whether your idea is even going to work. And so a lot of times you do it in simulation. And here you're seeing those errors accumulate, the position error. And yeah, this was a very important paper in the field of swarm robotics, really because it demonstrated, that swarm robotics is something that you could actually implement. It wasn't something that is necessarily limited to just software. And really doing it at this really massive scale is something that had not been shown before. So yeah, self-assembly in 1,000 robot swarm. It's a really important, really interesting paper in the field of robotics. So does anyone have any questions about this one? I can. Yeah.
Yeah, so for the robots, they're basically only controlling when the robots start and when the robots end, but not anything in between.
Yeah.
Because it's basically just going straight and taking
Yeah.
turns on its own.
Go fast, turn right. Yeah, it's the opposite of NASCAR.
Okay.
Yeah, so basically these robots are NASCAR. But, cool. We'll have pizza now.